The first subject that we'll bring up is some basics about photons and electromagnetic radiation and Kirchhoff's laws, which were the first insight as to how one might use spectroscopy. This picture here is of Josef Fraunhofer, that's the young guy, showing his spectrograph to senior scientists back in 19th century. He was the first person to take astronomical spectrum of the sun, and he saw lines which were then called the Fraunhofer lines, and you will see them shortly. So as you probably know, energies of photons are proportional to their frequency. Frequency and wavelength multiplied together give the speed of light. And the constant of proportionality is Planck's constant, and value is given here. Now, we often use energies expressed in electron volt units, which is the energy electron gets if it's accelerated with a potential of 1 volt. And it's this many ergs or joules. Typically, spectroscopic transitions or energies of photons of visible light are a couple electron volts, few electron volts. In the X-rays, we're talking about kilo electron volts and up, and gamma rays will be mega electron volts and up. So there are two important things to note here. First, even in classical physics, if you have charged particle like electron moving, if it's somehow accelerated or decelerated, that is going to cause it to radiate in electromagnetic waves. And then when you look at quantum systems such as atoms, right, they have discrete states of energy, and that comes in well-defined quantities depending on what the internal structure is. So electromagnetic radiation then comes really in two flavors, as continuum spectrum, that there are photons of all different frequencies, and as discrete ones, which are spectroscopic lines. It could be absorption or emission, depending what happens. There are several different ways in which continuum spectrum can be produced. The most common one is thermal spectrum. Any body with temperature greater than absolute zero, that will be all of them, emits radiation over all frequencies, and we'll discuss that spectrum shortly. But there are also other mechanisms like free transitions or breaking radiation. Cherenkov synchrotron will come up to this. Now, the important thing is that different processes in nature generate electromagnetic signals at different wavelengths. And because of that, we can use what we observe as a diagnostic of what's going on. So if you look at global electromagnetic spectrum like this, and this is in logarithmic scale, obviously, and so you can look where do different phenomena play a role. And typically, atomic levels, energy levels that correspond to most transitions are around visible light, give or take, UV, near infrared. So isn't that very fortunate, because we happen to live around the star that peaks right there. Now, as you go toward higher energies, then you start to see energy transitions of innermost shells of heavy elements, and then deeper yet into nuclear energy transitions, and then annihilation, things like that. On the other side, as you go to lower energies or longer wavelengths, you first see spectra of molecules and such, and then eventually just waves generated through different plasma processes. So you can see there's a broad range of different physics that plays a role here, and so by observing it at different wavelengths, then you can learn something about the source. The way we measure things is with spectrographs, and everybody's seen pictures of Newton with a prism making a rainbow spectra. There are almost no prism spectrographs that are being used anymore, because a much better way to do it is with diffraction gratings. And skipping over a lot of details, the way this is done is that diffraction grating is a piece of glass or metal on which there are little parallel grooves, each of which acts as a little mirror. And then bouncing light off of a diffraction grating at different angles, you see light of different frequencies will be phased in by different amount. So a given wavelength will from all refraction from different grooves will have constructive interference in some spot in the focal plane. But a different wavelength will be a little off because the wavelength is a little shorter. Now, this can be worked out in great detail, but intuitively, this is what's going on. So typically, what we have is some sort of entrance aperture. Otherwise, everything will be smushed together. And usually, a slit is used, so you get spatial resolution along one axis. And then there is an interplay. The wider the slit, the more light you get, but lower spectral resolution you have. Then that's collimated. That is, there is a set of lenses that makes this converging beam from telescope into parallel beam. It's the parallel beam of light that has to be bounced off the grating, and then has to be focused onto a camera detector such as CCD. So essentially, that's how most spectrographs work today. And when you go to Palomar, you'll see one of them. So what are Kirchhoff's laws? These come from 19th century. Before there was any atomic physics, before people understood any of this stuff. They played with Bunsen burners, putting different materials and looking what the spectrum looks like dispersed to prism. So if you have a hot flame or a hot body that radiates thermally, then there'll be a continuum. There'll be light of all different wavelengths. But now if you pass this light through a cloud of some gas or vapor, and you look light that passed through, you'll see that there are some wavelengths that are missing, that there is light being absorbed in particular wavelengths, which are characteristic for a given element or compound. And on the other hand, if you don't look at the continuum light, but look at the hot cloud of gas from side, you'll see it shining at those exact same wavelengths. And so the Kirchhoff's laws, and the name is Kirchhoff, not Kirchhoff, are these. So first, any hot and opaque body emits in a continuum, and then a hot gas that's transparent will shine in particular set of wavelengths, the emission lines, whereas cooler gas or gas that's been transparent, you look through it to some continuum source, shows absorption spectrum. And those wavelengths are characteristic of a given element or compound or ion. Now we, of course, completely understand where does this come from, but back in 19th century, nobody knew. And until Bohr figured out how atom of hydrogen works, spectroscopic lines were a complete mystery. There was a lot of empirical data, and people just didn't know where they come from. So typically what we do is we take spectrum of something, could be a star or a galaxy, what have you, that's dispersed, and then we compare that with spectra of laboratory sources like arc lamps and such to calibrate it. And then we can compare depth of different lines, which then tells us about physical conditions in the source itself. So things that you can get from a spectrum are temperature and composition of the source, say solar photosphere, but also you can measure velocities because you can compare wavelengths of the observed lines with those that would be at rest, and simple Doppler shift formula would apply. So spectroscopy then tells us about the physics of what's going on. It also tells us how fast things are moving in radial direction, and that has a great applications in cosmology because that's proportional to the distance. So here are some of the typical spectra they can see with emission or absorption lines superposed in continuum, depending what lamp they used. And every element, again, has its own characteristic signature, but the relative strengths of these lines will depend on the temperature and other physical conditions. So here is the solar spectrum. Now this one is really folded many times. You can think of it as kind of zigzag spectrum. The way this is done is with so-called a shell spectrograph, which is a way to do a lot of high-resolution spectroscopy in a single detector. And the black blotches are Fraunhofer's lines. He couldn't resolve the very faint ones with his apparatus, but he's certainly seen the big ones and gave him names, A, B, C, D, and so on. And sometimes we actually use some of his names, like H and K lines of calcium are Fraunhofer's lines. A and B bands are not from Sun, they're actually from Earth's atmosphere. C is now known as H alpha, and so on. We'll speak about how they come to be in a moment, but there is one other important question, like how is something going to be transparent or opaque? And here we talk about optical depth. Optically thick is a medium that is opaque, that photons are just scattering so much that you cannot see through it. So fog will be a really good example of that. Optically thin is a medium through which photons can fly with just a minimum amount of scattering or interaction, like air in this room, for example. Generally speaking, optical depth tends to be proportional to the density, so denser plasma will tend to be more opaque, and that governs a lot of physics of what happens inside the stars. So typically, a star is a ball of hot gas or plasma, and in its interior, it's optically thick. So when you're looking at a star like Sun, you're seeing a continuum source that has certain temperature and surface, like 6,000 degrees Kelvin. And then the outermost layers are radiating away, so they're cooler. And so that cooler gas, according to Fraunhofer's laws, will be imposing absorption spectrum. So the spectrum of the Sun is the spectrum of the outermost thin layer of plasma on the Sun. And the same is the case for just about every other astronomical source.